Welcome to Breadboarding. This is video 10 in the Breadboard 8088 PC series, and in this video we'll be continuing the previous videos where we added an LED display and keypad, and we're going to be looking at writing the software and testing the display and keypad in this video. Now we kind of run out of time to look at the Fritzing plans which I used for doing the stripboard design for the display and the keypad, so we'll have a look at that in a few minutes. Then we're going to go on and look at the test program written in 8086 assembler, and I'll be looking at how to convert that from 6809 assembler. Then we're going to program the EEPROM, and then we'll check to see if the display and the key codes are actually returning what we expect. First of all, let's just have a quick look at the board where we last left it. Okay, so we have the LED display over here, and we've added an extra 2 digits here into the configuration. So previously the previous Nanocomp 6809 would only address the first 6 segments. Now we've added the last 2 as well, so that now means we can do all 8, and we've plugged in the keyboard. Everything's in okay as we left it. The only thing I did notice after I'd finished the previous video is I'd forgotten to put in the resistor array here for the pull-up resistors. So that's basically the pull-up resistors down here. So now that's been plugged in, so we can do that. And without that, basically the segments wouldn't actually illuminate on the display. I did also need to do 1 or 2 other fixes, and I'll cover those when we come to do the software programming. So let's have a look at the plans for the keypad and display in Fritzing. First, we just need to have a quick look at some of the configuration of the keypad, just so when we're looking at the plans it all makes sense. So we can see here that the Q0 to Q3 output, that the yellow wires going down the keypad here are actually the Q0 signal, and we'll also be looking at PA0, and that is the row of keys going across the keypad in this way. Should just say that the diagrams on this side are looking from underneath the keypad, and this is looking top down from the keypad. And these are the key codes that when we actually come to test the keypad, these are the key codes that the Nanocomp software expects to have coming back. So this is Fritzing. It's a open source software. You do have to pay about €8, I think, to download it, and once you've got the link then you can continue to use that to get updates. So there was an update fairly recently. Now it is possible to do breadboard designs on this, but the only issue really with that is that you can only use 1 breadboard, whereas the stripboard layout's a bit more flexible. You can make your stripboards quite a decent size. Now what I was just going to show you is if we wanting to have a look at this, we've got the individual key switches here, and we can see where the wires are, so we can see the yellow wires going down here. One of the neat features is if you click on a particular pin here, you can actually see all of the parts of the board which are wired up, so we can actually see that the Q0 is going all the way down to those yellow ones, and you can even see when we look at the individual key switches, you can see the pins on the side of the key switches are being highlighted. And if we also then looked at PA0, then you can see that the key switches going from R across to 5 are also selected there. So it's quite neat for working out whether you got your wiring correct. And it's also possible to turn off certain layers. So if you turn off the parts layer, then we can just see the wires. The only real criticism I've got of Fritzing is it's not very easy to see the brakes and the tracks. So you can see there's brakes and the tracks here, and it is also possible to join tracks as well. Although I haven't used that. What I have done is when I've printed these out, I've tended to mark where the brakes and the tracks are to be a little bit clearer. Now if we have a look at the LED display, again this is looking from the underside of the board, and this does mean that when you've got components such as these, so you can see here this is the 7-segment display, so you can see that's the B. Over here we have, I think, digit 1. And if you just hover over here, you can see what these things are. And again, similarly, what we can do is say if we want to look at digit 0, what's that connected to? Oh yeah, that's actually going up to digit 1 here. And if we were to look, say segment A, where is segment A? Right, that's the second one in from the top. And is that A? Yep, that's A, and that's A. So again, this is also possible to turn off the parts layer, and it makes it a bit easier to see how to do the wiring. You can see here we've got some brakes and the tracks here between 2 sides of the pins. So I use this for doing the stripboard layouts. I do have another version of this where I did a stripboard version for the previous version of the project. So you can see here I actually mounted the displays on a bit of strip board, but this was really getting a bit messy. And also I needed to add extra chips here, so I didn't have enough space really to do this. So I'm not going to really use Fritzing for doing breadboard layouts. I'm only going to use it for strip board layouts in the future. So in the slides, what I have done is I've included PNG exports of these designs. So this is a view for the underside of the strip board, and then this is the view with the components removed, the parts removed, and you can see there those are where I've put X's where all of the breaks in the tracks are. Similarly, this is the LED display viewed from underside, and again where the break in the tracks are. So one thing I just need to show you, I did come across a mistake I'd made in the configuration of the decoder, address decoder, and this was the main address decoder, and the problem was that the chip enable for the PIA and also the serial port, though we're not using that yet, had an incorrect condition on one of these lines here. So the A16 originally was the not A16, and in fact we needed it to be A16 to make that an address D0000. So that was a correction I had to make to that. Now if we go back to the original Nanocomp monitor, so this is the assembly language for the 6809. You can see here before this there was a load of sample programs which you don't really need to worry about. But in fact, when we look here, it starts at 1100 and goes down to about 1800 lines. So there's about 700 lines of code here. And in fact, in doing the test software, what I've ended up doing is converting about 600 lines of this code. So what I may very well do, rather than going to C, it turned out to be a bit easier to convert this code into 8086 assembly language than I thought it was going to be. And what I have done is produced a sort of a spreadsheet just to help me, but it may be of interest to other folks as well. So this lists all of the 6809 instructions down the left hand side here, and obviously where there's different registers and parameters, and they've all been grouped together, the description, and then I have a list of all the 8086 instructions down the right here, and then I've mapped the 6809 ones to the 8086 ones. Now most of these there is actually a pretty straightforward mapping. There's a few, ABX is kind of like an old 6800 series, I think, instruction for compatibility. There are a few areas that the bit test in the 6809 is not completely the same from what I can tell from test, and branch never is kind of like a 2-byte no-op, so that doesn't exist. And there's no clear function in the 8086, so XOR is used. If you XOR a register to itself, then that will effectively clear it. And the wait function is similar to sync, but it waits for the test, not the interrupt. And you can sort of see where the 8086 instructions, where there isn't an equivalent in the 6809, so a lot of ASCII related adjustment things, the string handling routine, so there's quite a lot of string handling routines, decimal adjust after subtraction, divide, we don't have anything in the 6809. There aren't any parity flags within the 6809, and a few other things. So the vast majority of the instructions that we like to come across in the 6809 do have an equivalent in the 8086. And so by doing this, I've been able to convert the software from the 6809 version into the 8086 version a bit more easily than I had otherwise anticipated. What I have tended to do is the 6809 A register tends to go to the AX/AH, the higher byte, and the B register tends to go to the AL, the lower byte. And that's similar to the way how A and B are mapped to the 6809D register. And then I've also been mapping X and Y to some of the other 16-bit registers. So let's have a quick look at the test code. So this is the LED key test assembly program. So it's been based on the RAM-ROM test one that we did in the earlier videos. It's assembled using NASM, and so that's the command line for it. What we've got here basically are the 7-segment display values that are needed to display the different characters we've got there. Then we've got the different code that should be expected to be returned back to the Nanocomp monitor for the various keys as they're pressed. And if you remember in the diagram, I've put the key codes in the keypad diagram. We then actually got the start address is still the same as it was before, so this means that the EEPROM is going to be based at F8000 in the memory map, and I've also defined the display buffer to start at the top of the 512k RAM. That's going to be at 7FFF0. And then we've got the port details for the PIA. The only difference really here is that because I've mapped A0 to RS0 and A1 to RS1, unlike the original Nanocomp, then this means that the port mapping here is slightly different from the original Nanocomp, but should be less likely to make mistakes when wiring things into those pins in the future. So as far as the software is concerned, we start at the bottom as we did in the previous one. So the initial reset vector, as it were, which is at FFFF0. And all this is doing is in fact jumping to our test start. So this is where the 8088 goes to start the first instruction after reset. They basically send us back to the beginning. And all I'm doing here is initializing the stack. So we're setting the stack to start at the top of the RAM. And in fact, I've given a sort of 256 byte area at the top of RAM that we can use for the monitor. And so the stack starts at 7FF00 downwards. So we've got enough space there. We're also defining the various data segments, stack segments, and also initializing some of the variables here. Now, to start with, very simply, all we're going to be doing here is moving the word Nanocomp into the display buffer, and then we're going to just call this dispress routine, which is the same name as the original Nanocomp monitor, and then we're going to call the get key command. So effectively this will be displayed until such time as you press a key, and then after that we're going to do a load of tests. So we're just going to test that our right hand byte handling for the 7-segment display, so this takes 2 digits for a byte, and the right hand one gets converted into a 7-segment display, and we put these out here. So this is 0 to 7, then we're doing 8 to F, and then we do it for the left hand byte as well. So that's just testing that the routine here has been converted properly. And then once we've done that, we then clear the display out, just set spaces, and then all we're going to do is call get key, and then all we're going to do is display what the code, the byte values of that code are. Given that we've already tested the left 7-segment and the right 7-segment routines, and we should by here know that we're getting everything right. So when I've actually gone through and converted the routines, I'm not going to go through every single bit here, but what I've done is I've ended up pasting the original 6809 code in here, and then I've done some sort of conversion in line. So for example, clear A is X or AX with AX. Now in general, where we've got A's and B's in here, I've tended to use the AH as A and AL, the lower byte, is B, and that's the same mapping as the 6809D register. And basically this was a bit easier than I had anticipated it being, and seemed to work with virtually no problems first time in this particular code. The key handling routine was a little more complicated, and the main issue here is that on the 6809, whenever you do quite a lot of operations, including load in particular, will actually set the various 0 flags and other flags and indicators. The issue here is that when you do things like knots and moves, then these indicators are not set automatically, so we had to add a few compare instructions where the conditions were not being detected automatically. So there are some differences in the way how the two processors work, quite understandably, and getting to grips with that just took a little bit of time to work out what was going on. And now I know that the some of the shift instructions in 8088, 8086 is possible to actually provide the CL parameter, CL register to provide a value, but for the moment I've just kept things simple and just trying to match across to the existing 6809 code. So basically all this code is being converted across from the 6809, and I'm not trying to optimize it. I'm not trying to really use any clever features. very much trying to keep it as similar as possible. And then we've actually got two tables in here. We've got values of the key codes that we defined above and values of the 7-segment display. So these are used by these routines that convert the various sort of keyboard inputs and 7-segment lookup codes and things. So that's the software. All you need to do is assemble that. Okay, so the few warnings with our macros are padding out the code here. So if we now go into XG Pro, so we've got the ROM type loaded here. We'll just put this in to the programmer. I'm going to take that out of the zero insertion force socket and put it in the programmer. Make sure all the pins are in properly. Recommend we always read the existing version of it, so we'll have an earlier version of the code here, and then we'll just program this. So it all looks like it's all done okay. So let's now put the ROM back in. Okay, and we're now all ready to run things. So what I will just do, I've got the printout of the keypad diagram. So this diagram here shows the keypad and what the scan codes which are expected. So what we're expecting here when we turn this on, it should boot up and actually show just Nanocomp. And then as I press keys, it should go through and test out the two 7-segment conversion routines. So it's just going to show us 0 to 7, 8 to F, and then do that again. And then after that, then each time we press a key, then we should get the key codes here. So let's see if this is working. Excellent. So sometimes if a wire's come loose, particularly down the bottom here, you might have one or two of the segments might disappear. So for example, if you get sort of that sort of thing, it tends to be that a wire has come loose. But that's working okay. So we're just going to test the 0 to 7. So they're all coming out. I just wanted to do that to make sure I hadn't made any mistakes in the conversion, so that I was using these routines to actually do the keypad codes. I just wanted to make sure that it was all working. So 8, 9, all the way up to B, C, D, E, and F. And then this is the left-hand digit, that the same routine, and that all seems to be working. So now what it's doing is waiting for me to press a key. So what I'm going to do is to go through the top here, all the way down to the bottom here. The reset and the abort are hardwired into reset and the non-maskable interrupt, and those aren't plugged in at the moment, so we won't be able to test those. We're just going to go through this, so we'll just check these off to make sure everything's okay. Okay, 0, 5, 1, 5, 2, 5, 3, 5, 0, 3, 1, 3, 2, 3, 3, 3, 0, 4, 0, 1, 1, 1, 2, 1, 3, 1, 1, 4, 0, 0, 1, 0. It's a little bit sticky there. 2, 0, 3, 0, 2, 4, 0, 2, 1, 2, 2, 2, 3, 2. So all the codes are coming back. Okay, so that all seems to be working. Let's just reset it and get our Nanocomp back. What this means is that we should then be able to convert the rest of the 6809 monitor code into 8086 assembly language. I think it's going to be easier to do that using the mechanism I've shown you than probably trying to go down the C approach. So in the next video, I'm probably not going to convert the original Nanocomp monitor into C. I'm probably just going to continue with my conversion of the 6809 code directly to 8086 code. So that will be in the next video. So if you don't want to miss out on future videos, please hit subscribe. And if you found the content interesting, useful, please hit like. It just helps to make the videos available to a wider number of people. Thanks for watching.